So hello everyone, welcome back to the channel. Today we are going to solve the problem shortest xy distance in a grid. So given n cross m grid of characters 0, x and y, find the minimum Manhattan distance between x and y. So Manhattan distance is given like that. So let's discuss the question. Like we are given the n cross m grid. So initially in n cross m grid, we want to minimize the Manhattan distance. So Manhattan distance something like that. Let's say we have 2 points x1, y1 and x2 point y2. So Manhattan distance will be equal to x1 minus x2 plus y1 minus y2. This is the Manhattan distance, and we want to minimize that. But between what? We want to minimize the Manhattan distance between x and y. So let's say we are at this x. So initially when we are this x, so this x and this y, we have to find Manhattan distance between these two x and y. Then this x and this y. So we have to find the Manhattan distance between them, and we want to find as minimum as possible. So first discuss the Manhattan distance in a shorter form. So let's say I am at x comma y. So I am allowed four directions for moving from x to y or y to x. We can travel in four directions: x minus 1 comma y, x plus 1 comma y. Because I can go above, I can go down, I can go left. So for that, x comma y minus 1 and x comma y plus 1. So we will observe that the Manhattan distance between xy and x comma y plus 1 will be 1. Why? Because x minus x plus y minus 1. This minus plus minus will become minus, and then we have 0, then mod of minus 1 will be equal to 1. Similarly, we will find that Manhattan distance between all is 1. That means our question boils down that we have to find the minimum steps to reach y from x, or we can say x from y. Let us consider the question that we have to reach minimum steps to reach y from x. Okay, so if I want this x to reach this y, so one step. Manhattan distance between x and 0 is 1. We can say one step. 0 and y is 1. So two steps are required for x to reach y. Okay, now similarly this x, if I go to this x can reach in one step here, then in one step here. That means two steps are required here. But if I want this x to reach this y, one step, one step, one step. So 1 plus 1, 2, 2 plus 1, 3. Three steps are required. So we can say that at minimum, two steps are required for x to reach y. So this is a basically question. Our aim is to achieve minimum steps to reach x, to reach y from x, y from x. Okay, so let's understand the intuition behind this question. So initially we are given this n cross m grid. So let's understand that how can we approach this question. So whenever we want to find minimum distance also, since there is uniformity, because we are always moving by one step, one step, one step. So here is uniformity. So here comes BFS algorithm will properly work. But when there is no uniformity, like we have minimum, we want to find minimum distance, but there is non-uniformity, like 1, 2, 3, 2, 1, like we have to 1 distance, 2 distance, 3 distance, 2 distance, like the graph question video. So in that case, we use Dijkstra. Since here uniformity, we can apply Dijkstra algo, but why to increase complexity? So let's use the BFS algorithm here. Okay, so let's do this question using BFS algorithm. So we are given the n cross m grid, and we want to minimize the Manhattan distance between x and y. So let us consider that we are initially at x here, like so 0 comma 2. So let us consider we are initially all the x. Let's say I am at here, I am here. That means at step is equals to 0, we are at here. Now at every point where I can go above, left, down, and right. So from this position, I can go down, and from this position, I can go here, but there is no need to go. Okay. Now, why? Because let's say I am here and I am here. This x will reach y. This x will take extra step to reach this x, and then it will reach y. So since this x is more closer to y, so this can reach y more easily. Why should this x be taken to this x, then this x will take to this y? So better is to take this x to reach this y. That's why whenever we take x, we do not visit that x again. So initially we are at this. Now at step is equals to 1, we can come here. Similarly, this x can go here, but we said that we do not require. Similarly, this x can go here, but this is invalid. Above, invalid, can't go. Now similarly, this x can go where? Here as well, here as well, and here as well, but here and here as well. This is invalid position. We will not take it. Now this is x is already visited. That means this x, like if this x is finding y, okay, then why should this x can go? Because if this x, let's say, find two distance, it will add one distance, three distance. But this x is more closer, na? That's why we do not need to take this x. So now this x can be this 0, they are not visited, so we will take them. Now, so at step is equals to 1, we can reach these zeros. Now at step is equals to 2, these zeros can be reached to this y. At step is equals to 2, these 0 can reach to this y. This 0 can reach to also this y. It is already visited as such. This 0 can already visited. This 0 will reach this y. So we can say at step number 2, we can reach this y. So at this point, we will return the answer. Why? Because we have reached the y in 2 steps. So why to go ahead? Because we have found the answer. So that is the approach behind BFS algorithm. So how can we approach? Like here we will create a queue of pair intent. So initially in queue, we will add all indices of x. Let's say here 0, 0, 0, 1. So at step number 0, we will add 0, 0, 0, 1. Now at step number 1, we will go to add 0, like this one 0 will come. Because that's step number, this will become 1, 0. We are going more closer to y, and we can reach this 0, 1, 1, as we have said. Similarly, we can reach this 0 in step number 2, 0, 2. Now at step number 2, in step number 2, where we can go? We have reached the y's 1, 2, 2, 0, 1, 2, 2, 0, and many positions. But here we can see we have found the y. So we will return from here. That is step number 2. We have reached x, we have reached y from x. Similarly, if we want to calculate x from y, we can also do this. We can store in q y's, and then we can reach x. So it's up to us. How can we do this implementation? So let's discuss the code. Like firstly, I will create a queue initially. Now we are creating a visited array. Now, why we are creating this visited array? So let's say I am at this 0. I am at this 0. And this 0 will, uh, here, this y is here. So let's say I am at this 0, and this 0 will say that I am coming here. Then it will come back there. No, it will go down. So what will be better? One step or three step? Obviously one step. So Whenever we have, because this 0 will be already visited. So why we need to take this? Let's say this here is x. So initially in Q, we add xx. Then after that, we will add zeros because they are adjacent. Now, this 0 will already be visited because we are taking in step number 1. But when this 0 will try to take it adjacent, this 0 will take that this 0 I can take. But this 0 is already taken at smallest step. So we do not need to reach it again and come back and then reach y. So that's why we are creating the visited array. So like here we are getting the visited array. Now we will traverse the loop, and if grid of ij, we are adding all the x initially in the queue. Queue push I comma j. Visited of ij is equals to 2. Okay. Bx of 4 minus 1 0 1 comma 0. And because we can go in 4 direction, so we can go in 4 direction like I'm at x comma y. I can go at x minus 1 and then y, or I can go x comma y plus 1, or I can go x plus 1 comma y, or I can go x comma y minus 1. Okay, so dy will be a 4 direction 0 minus 1 0 1. Okay, now initially let's say our distance is equal to 0, or we can say steps is equals to 0. So while until our queue doesn't become empty, we will take it is equals to queue front and pop it from the queue. But since we have to traverse each and every level, so we will until our queue size is traversed. That means one step is traversed. Till then, we will traverse the queue. So now, uh, here when we pop out from the queue, so point will be x. Let's say row number is this and column number is this. So I can go in 4 direction at this point, 0 to 4. So at every point, what will be adjacent I? X plus dx of k, okay? And adjacent j is equals to y plus dy of k, obviously, because if I am at x comma y, so I can go x minus 1 comma y, x comma y minus 1, x plus 1 comma y, and x comma y plus 1. So if the position is valid, that means adjacent I is greater than is equals to 0, adjacent j is greater than is equals to 0, and adjacent I is less than n, and adjacent j is less than m, and visited. And if it is already visited, we don't have to take it. So we have to check if it is not visited. If it is not visited, then we will be able to take it. Now, if all conditions are fine, then we will say that we can insert it into the queue, and then we will mark this as visited. Now that we have taken at smallest level, so why to take this at higher level? Obviously. Okay. Now at every level, this is a level whenever we travel queue size. Now after every level, we will increase the steps. Okay. And at the end, we will return minus 1. But we have not written yet the condition that when we find y. So let's see. Here I am adding the condition that if x is equal to, that means grid of x comma y is equal to y. That means return the steps, number of steps that are taken to reach y. So let's compile and run the code and check whether it's working fine. Yes, let's submit the code. Yes, it is properly working fine. If I change this to y and if I change this to x, that means I am adding all y's in grid q, and then we are reaching x. Then it will also work. So I have checked this already. Um, Obviously, it will work because anyone can reach anyone like this is the. So this is all about the code. So this question was all about BFS, that is finding the minimum distance since in uniformity is there. So normal BFS will also work. So thank you. Have a nice day.